Welcome to all of you. Now we discuss MCQ of the paper CC-6 Mathematics Honors 2020 Ring Theory and Linear Algebra 1. Question paper of 2020. Question 1a. The ring of matrices S is the set of 2 by 2 matrices AB, 2BA such that AB belongs to the set of real numbers R, contains, correct option is 2, divisors of 0 with unity. Let capital A is a matrix 2 by 2 matrix A, B, 2B, A, and capital B, C, D, 2D, C, and both that belongs to the ring of matrices S, where A, B, C, D belongs to the set of real numbers R, with AB not equal to 0, 0. That means A and B not simultaneously 0, 0. Either A 0 or B non-zero or B 0, A non-zero, or both non-zero. That is, A is not a zero matrix, 0, 0, 0, 0. Let AB equal to O, null matrix. This implies AB 2BA, CD 2DC equal to 0, 0, 0, 0. Then by matrix multiplication, AC plus 2BD, AD plus BC, 2BC plus 2AD, 2BD plus AC equal to 0. Hence, this AC plus 2BD equal to 0. This AC plus 2BD is same. And AD plus BC, this is also taking 2 common, AD plus BC equal to 0. This simultaneous homogeneous linear equation can be written as this. We interest for solve C and D. So in matrix form, A to B, B A. This is BC plus AD. BC plus AD. This is a homogeneous system of equations, linear equations for C and D. For non-zero solutions of the C and D, variable C and D, we have the rank of this coefficient matrix A to B, B A must be less than 2, the order of the matrix. Then determinant of this A to B, B A equal to 0, that is A square minus 2B square equal to 0. And for AB belongs to the real number, and for non-zero AB, we must have either A equal to root 2, B equal to 1, A equal to root minus root 2, B equal to 1, A equal to root 2, B equal to minus 1, and then A equal to minus root 2, B equal to minus 1. There are 4 options to satisfy this equation A square minus 2B square equal to 0. Hence, we can write root 2, 1 to root 2, this matrix, into this matrix minus root 2, 1 to minus root 2. This equal to 0, 0, 0, 0, null matrix. So S contains divisors of 0, because this matrix not equal to 0, this matrix not equal to 0, but this is 0, product is 0, multiplication is 0. So S contains divisors of 0. Now I is the identity matrix of product 2, equal to IA equal to A for any A belongs to the S, where I is the identity matrix. Hence, S contains the unity, that is multiplicity identity, and contains divisors of 0. So, this ring of matrices S contains divisor of 0 with unity. Correct option is 2. Question 1b. Which of the following ring is not an integral domain? Correct option is 2. Z6 plus dot. This plus means addition modulo 6, and this dot means multiplication modulo 6. Now, we know that Zn plus dot is an integral domain if and only n is a prime. And also, Z set all integers plus dot. This plus means addition modulo n. This dot means addition multiplication modulo n. But this plus is the addition of integers, and this dot is the multiplication of integers. Is also an integral domain. Now, Z6 plus dot is a commutative ring with unity. It contains divisors of 0. So, this Zn plus dot is integral domain if and only if n is prime. Here 13 is prime, 5 is prime, and also Z plus dot is not an integral domain. So, Z6 plus dot is not an integral domain because 6 is not prime. And because it contains divisor of 0, Z6. This is the class 2 belongs to Z6 and class 3 belongs to Z6. And class 2 into class 3 multiplication modulo 6 equal to class 6, that is equal to class 0. So, Z6 contains divisors of 0. Class 2 and class 3 are divisors of 0 in the ring Z6 plus dot. Therefore, Z6 plus dot is not an integral domain. Now, the set Zn is the classes of residue of integers modulo n, that is Zn is equal to class 1, class 2, class n minus 1, where the class A means the set of all those x belongs to the set Z, integers Z. A is congruent to x modulo n, that is A minus x is divisible by n, that is equal to k into n. N is the fixed positive integer and k is any integer. And plus n is the addition modulo n. For simplicity we write simply plus. Here class 5 addition modulo 3 class 11, that is equal to class 16, and this addition modulo 3, so 16 is divided by 3, then residue is 1. 3, 5, 15 and residue is 1, so this is equal to class 1. And dot n is the multiplication modulo n, that means class 5 dot 3 class 11, that is equal to 55 class, and divide 55 by 3 and 3, 18, 54, so we get the residue 1. This is the residue class 1. For simplicity we write plus n as plus and dot n as dot. So here Z6 plus dot means the addition modulo 6 and multiplication modulo 6. Next question, C. Let R be a ring where R equal to Z8, plus, dot. Then the characteristics R is, correct option is 3, 8. If R equal to Zn plus dot, then characteristics are equal to n. That is, characteristics are in n means n to class A equal to class 0. N into class A means class A plus dot dot plus class A n times. This is equal to class 0. For all class A belongs to Zn, and n is the least positive integer. This n is the least point for which this relation holds. Now, Z8 is class set of residue classes, this class 0, class 1 to class 7. Hence, 8 into class 7, that is equal to class 7 plus class 7 plus class 7 up to 8 times. So this is equal to 56 class, and divide 56 by 8, we get no residue, 0 residue. So this is 0. And this class 8, 8 into class 6 equal to class 0, and so on, so on. So the characteristics of this ring Z8 plus dot is 8. Question D. Let S is the set A plus B omega such that AB belongs to set of real numbers R, and omega is the imaginary cube root of unity, minus 1 plus minus I root 3 by 2. So omega is the imaginary cube root of unity. Then correct option is 2. S is a subfield of the complex field this C. Now we have a theorem. Let S be a subset of a field F. Then S is a subfield of F if and only if the maximum if the number of elements S is greater than or equal to 2. That is the we write cardinality of S. Cardinality of S greater than or equal to 2. At least there are 2 elements in the set S, and A minus B belongs to S for all A comma B belongs to S, and A B inverse belongs to S for all A belongs to S, and for all B non-zero B belongs to S also. So this is the necessary and sufficient conditions for to form a subfield. Now 0 plus 0 omega belongs to S because the construction of S is A plus B omega, A B any real. So 0 plus 0 omega belongs to S, 1 plus 0 omega belongs to S. So we get at least 2 elements in S, in the set S. So cardinality of S is greater than or equal to 2. Here omega not equal to 1. And this the complex root, so not equal to 1. That is the complex root, cube root of unity. That is the root of the x cube equal to 1. Next, let x comma y belongs to S. Then x equal to A plus B omega and y equal to C plus D omega, say, where A, B, C, D belongs to set of real numbers R. So x minus y equal to A minus C plus B minus D omega belongs to S. Next, let y not equal to 0 belongs to S. Then, so we can get y inverse because y is non-zero. X y inverse equals to A plus B omega into C plus D omega inverse. That is A plus B omega by C plus D omega, multiply numerator and denominator by C plus D omega square. And after simplification, we get this. Here we use the result omega cube equal to 1 and 1 plus omega square equal to 0. So here we put omega square equal to minus omega minus 1. And then we simplify this, and omega square plus omega equal to minus 1 put here. So we get this AC plus BD minus AD whole divided by C square minus CD plus D square plus BC minus AD by C square minus CD plus D square into omega. Obviously, this is real number, and this C square minus CD plus D square not equal to 0. This belongs to S. Why this not equal to 0, denominator not equal to 0? Because y not equal to 0. So y means this C plus D omega. So obviously C plus D omega not equal to 0. And C plus D omega whole bar equal to C plus D omega bar, because C and D are real, and omega bar is the complex root 1 plus I root 3 by 2, so omega square equal to minus 1 minus I root 3 by 2, so this is equal to C plus D omega square. So C plus D omega not equal to 0, as well as C plus D omega square also not equal to 0, and multiply these, we get C square minus CD plus D square. So this is not equal to 0, this is not equal to 0, so this is not equal to 0. So denominator not equal to 0. Hence this element belongs to the set S. Hence by the previous theorem, S is a subfield of the complex field C. Previous theorem means this theorem, subfield cardinality of greater than or equal to 2, cardinality of S, A minus B and A B inverse for non-zero B belongs to S. A minus B, X minus Y belongs to S, and XY inverse belongs to S. Hence this. Note that let A be a field, a subring S of A is called a subfield of F if one F belongs to S. One F means the unity of F, multivariate identity. For each A, non-zero A belongs to S. A inverse belongs to S. So, a subring S is called subfield if one F belongs to S and A inverse belongs to S. Next question, 1E. Let R be a ring with unity element E, and let phi maps R to R dash be ring homomorphism. If phi E equal to 0, where 0 is the zero element of the ring R dash not equal to R, then kernel phi equal to the correct option 1, that is the ring R. Let small r belongs to capital R. This capital R is the ring, not real number here. Then phi r equal to phi r into E, because E is the unity in R. So phi r into phi E, because the definition of the ring homomorphism, phi is the ring homomorphism. It is given that phi is the ring homomorphism. And now this phi r, the phi e equal to 0, it is given that phi equal to 0. So phi r equal to 0 for all r belongs to R. Hence cardinal of phi equal to R. R is any element. So definition of cardinal is this: cardinal of phi equal to R, because smaller the elements of capital R, any element of capital R. So cardinal of phi equal to the ring set of the R, set R. Question F. Which one of the following ideals is not a prime ideal? Correct option is 2. 4z in the ring 2z, and all others 2z in ring z, all other are prime ideals, but only this option 2, 4z minus in the ring 2z is not prime ideal. In a ring R, an ideal P not equal to R is said to be a prime ideal if for A, B belongs to R, AB belongs to P, either A belongs to P or B belongs to P. The definition of prime ideal here. The ideal 4z, Z is the set of all integers, in the ring 2z is not prime ideal because 2 into 2 belongs to 4z, but this A, B belongs to P implies either A equal to P or B equal to P, but 2 does not belongs to 4z. So this correct option is true. Question G. The dimension of the vector space complex field C over the real complex vector space C over the real field R is option 3, 2. Dimension of the vector space, complex vector space is over the uh, real number R. C is the complex number set of complex numbers. This set A plus IB such that AB belongs to the set of real numbers and I square equal to -1. Now 1 plus I0 and 0 plus I1 belongs to C, set of complex numbers. Then for any A plus IB belongs to complex number can be written as A into 1 plus I0 plus B into 0 plus I into 1, where AB belongs to the set of real numbers. So any complex number can be written as a linear combination of these two vectors, 1 plus I0 and 0 plus I1. And the set S, capital S, this 1 comma I0 comma 0 plus I1, these two vectors here, there is two complex numbers, S is a basis of the complex set vector space C over R. This set S is linearly independent vectors 1 plus I0, 0 plus I1, and this set S generates the whole complex space C. And so dimension of the complex complex vector space, this over the real vector space over the complex numbers equal to 2. Question H, let V be vector space of all 3 by 3 real matrices over the field R, real field R. The dimension of the subspace W consisting of all symmetric matrices is, correct option is 3, that is 6. Let V be the set of all 3 by 3 real matrices, say A1, B1, C1, A2, B2, C2, A3, B3, C3, where AI, BI, CI are all belongs to the set of real numbers for I equal to 1, 2, 3. Then VR is a real vector space here, and W is a real symmetric matrix. Real symmetric matrix W equal to ADE, DBF, and EFC. Is a symmetric matrix, and A, B, C, D, E, F are all belongs to the set of real numbers. This 1, 2 position equal to 2, 1 position, 1, 3 position equal to 3, 1 position elements, and these 2, 3 position equal to 3, 2 position elements for symmetry matrix. Now, WR is a subspace of VR. Let E1 is matrix 1, 0, 0, 0, 0, 0, 0, 0, 0. E2 is the 0, 0, 0, 0, 1, 0, 0, 0, 0. E3 is the 0, 0, 0, 0, 0, 0, 0, 0, 1. E4 is the 0, 1, 0, 1, 0, 0, 0, 0, 0. E5 is the 0, 0, 1, 0, 0, 0, 1, 0, 0. And E6 is the 0, 0, 0, 0, 0, 1. Sorry, 0, 1, 0. This is the wrong. Actually, this is remove this vector. This vector, remove this. 0, 0, 0, 0, 0, 1, 0, 1, 0. Let S is the set of all these 6 matrices E1, E2, E3, E4, E5, and E6. This set S is a basis of WR. WR, and this is the linearly independent and this generates the W. So the vectors generates W. Hence the dimension of W are equal to 6. Question I, let T maps R4 to R4 be a linear mapping. The nullity of T plus rank of T is, the correct option is 4. That is 4. Let V and W be a vector space over a field F. T maps V to W be a linear mapping. Then kernel of T is the set of all those alpha belongs to V such that T alpha equal to theta dash. Theta is the null vector of W. And image T is the set of all those T alpha such that alpha belongs to V. And kernel T is a subspace of V. and the cardinality is called the nullity, null space of T. The dimension of cardinality is the nullity of T, and image of T is a subspace of W. So dimension of cardinality equal to the nullity of T, and dimension of image T is the rank of T, and dimension of cardinality plus dimension of image T equal to dimension of V. So nullity of T plus rank of T equal to dimension of V. Here V equal to R4 and W equal to R4. Hence dimension V equal to dimension of R4 equal to 4. Hence the correct option is 4. Last question J. If lambda is an eigenvalue of a real skew symmetry matrix, then modulus of 1 minus lambda by 1 plus lambda equal to the correct option 2, that is 1. Theorem: the eigenvalues of a real skew symmetry matrix are purely imaginary or 0. And this is the real analysis schema, page 211. This is the result: eigenvalues either purely imaginary or 0. If lambda equal to 0, then 1 minus lambda by 1 plus lambda equal to 1, modulus of this 1. If lambda equal to purely imaginary, equal to IA, and A belongs to real number. So we get is 1 minus IA by 1 plus IA, and multiplying numerator denominator by 1 minus IA, and after simplifying this we get this. This is x plus iy, modulus of x plus I equal to root over x square plus y square. So this square plus this square, root over of this, and after simplifying we get the result 1. This completes the MCQ 2020 CC-6. Thank you for watching this video.